Well, hello all. Welcome to this concept on orbit eccentricity. So we'll try to derive an expression of orbit eccentricity in terms of energy and angular momentum. Okay, and there are various other parameters will come into picture. So we'll see accordingly. So without wasting much of our time, let's get started. Now, I have considered a part of an ellipse. Okay, this is a elliptical profile. So you can take as a circular profile. Okay, it's up to you. So probably in order to have a quick generalization, we have taken elliptical profile. Now, as you see, we have a very big mass, which is the sun. So here we'll take the planet and the sun combination. So we have uh, sun over here and planet started to revolving. So this is going to be my A. So that is a position. Okay, from the focus to this axis. Now this is a meeting point of, let's say this is going to be a semi-minor axis meeting point. So if you draw a line from here to here, this is going to be a which we have already seen in our previous videos. And if at all you feel like to go and check, uh, please try to revisit and get some insights. Okay, now here we already know that there are different sort of uh, position that we are come across. We have the foci here, so this is not a vacant foci, is it not? So your this plant position can be here as well. So it's all dependent on the path how it is being traced off. Okay, so here we are more interested about the deriving the equation. Okay, so for that we have the kinetic energy which is been revolving. Okay, the kinetic energy exhibited by this uh, planetary body which along this path is going to be ke. Let's say this is going to be ke kinetic energy, which is given by half mv square, the basic physics. So the basic physics laws we'll try to apply here. Okay, we are not going into a deeper aspect of integrations and differentiation, but still in the preceding videos we'll try to go at the advanced level. So this is just to understand the concept. So we'll proceed accordingly. Now we have the gravitational potential energy which is given by, okay, gravitational potential energy, okay, which is given by uh, your gravitational force into the distance a. Okay, so this is going, definitely it is going to be a negative quantity, as you know, because this a is, or this a is having a separation from the bigger mass and the smaller mass. So this is within the gravitational field. Okay, so there is always a work done which is moved against the gravitational field, that is called the gravitational potential energy by definition. So definitely this is going to be a negative quantity. Okay, so because work is done against the gravitational field, so we know that according to Newton's law of gravitation, Fg's can be written as gmm divided by a square in this context, and we have one more a here. Okay, so this complete term, okay, you can write Fg into a or something, so that will give me the gravitational potential energy, is it not? So if you cancel one over a over here, you are going to get minus of gmm divided by a. Okay, so this is more clear actually, is it not? So your gravitational potential energy, you simply write the potential energy is going to be minus gmm divided by a. And now we know your gm, so that we have already seen. Your gm is actually your gravitational parameter. Okay, and now that you can substitute over here, this is going to be minus of mu m divided by a. Okay, so that is your potential energy. Now going back to kinetic energy experienced by the revolving mass of m and the orbiting velocity v. So this also can be written. If we have revisited our video, we have already we have derived an expression for v square, which is in terms of the gravitational parameter, and in fact to the distance of separation. So that is called mu by a. Okay, I hope that is more clear actually, is it not? So so if you substitute the v square term over here, okay, this is more a bit of clear over here, is it not? If you substitute the v square term, this is going to yield me kinetic energy is again equal to half into m into mu by A. Or this is something like m into mu by 2A. Okay, I think this is clear now. Now the total energy, let it be E total, can be represented by total potential energy or the potential energy plus kinetic energy. And now you sum it off, you get minus mu m divided by A plus m mu, it's all the same, by 2A. Okay, if you take the common denominators, okay, you need to multiply 1 2 and divide by 2 here. Now this is going to yield me minus mu m, okay, divide by 2A. I think hope this is clear, is it not? So simply we have done some adjustment. We have multiplied on the top and you divide by on the bottom side. So we do the normal subtraction, which will yield me minus mu m by 2A, is it not? So that is the total energy which is being exhibited by this revolving planet. Okay. Now if you see the planet, so this is the total energy which is being uh, at this point. The energy can be written as E total is equal to minus mu m divided by 2A. Okay. So that is energy actually, is it not? So that is what we have derived over here. Fine. Now let us proceed with the further steps. Okay. Now we already know that we have a relation called R is also equal to h square by mu at any position divided by 1 plus e cos theta. Okay. And again we have an expression in terms of a into 1 minus of e square divided by 1 plus e cos theta. So this is one definition. So if we compare the both these two equation, okay, if you compare the two equations, the specific angular momentum square divided by mu divided by 1 plus e cos theta, and the a into 1 minus of e square divided by 1 plus e cos theta. So if you do a comparison, it is quite evident that your h square by mu will going to yield me a into 1 minus of e square, which is perfectly fine. Okay, here it is h cap square because this is actually your h corresponds to the specific angular momentum, okay, which we have already seen in our previous videos. Specific angular momentum, okay, which is a very important parameter as far as the rotational mechanics is concerned. Okay, for any revolving body there will be some angular momentum. Okay, now from this expression you can write what is a. So a can be written as h cap square by mu into 1 minus of e square. Okay, so from here you can write your a is equal to h cap square divided by mu into 1 minus of e square. Now if you closely observe, in your energy term you have an a term here, is it not? In your energy you have an a term here, so that a we can substitute here, which is h cap square, the momentum, the specific angular momentum square divided by mu into 1 minus of e square, is it not? So now I'll write the expression for the total energy here. So your total energy is going to be, I'll take this space, your total energy is going to be minus mu m by 2a, and if you substitute the value of a here, that is going to be minus mu m divided by 2 into, what is a here? A is simply but h cap square by mu into 1 minus of e square. So that we are going to put it over here. Okay, by mu into 1 minus of e square. Now this, the complete term is going to be on the top. Okay, so this is going to yield me minus mu square m divided by 2 h cap square. Okay, and you will get one more quantity here, 1 minus of e square. Okay, it's a simple math. The entire downside will be going to the upside, and we end up with 2 h cap square, which is in the denominator, and that will give me e total. Okay, now I'll write this one for better simplification. I'll write here your e total is going to be equal to minus mu square m into 1 minus of e square divided by 2 into h cap square. Okay, So here we have a negative here, so we go with mu square m into e square minus 1. Okay, we put this in bracket. Is it not? We applied a minus sign here. Divide by 2h cap square, which is equal to e. We'll write simply e. Okay, e total or e. It's okay, fine. Now you take this h cap square into 2 in this side, the left hand side. Okay, you multiply it. You're going to get e square minus 1 is going to be 2h cap square into e. Okay, and you take the entire term the down, you get mu square into m. Okay, on further simplification we get e square is equal to 1 plus 2h cap square divided by mu square m. Obviously there will be e, so mu square m. So 2h cap square e by mu square m you will get. Okay, now then e is going to be your plus or minus 1 plus or 1 plus 2h cap square e by mu square m. So I don't want a negative quantity to be here, so I always go with the positive value. So you get 1 plus 2h cap square e divided by mu square m. Okay, now this is called the orbital energy equation in terms of uh, eccentricity. So this is also called an eccentricity equation in simple words. So this is going to be my eccentricity equation. Okay, now let us do some analysis here. Okay, now let's say my energy. Okay, my energy level is going to be very much 0. Okay, now E is going to be 0. The orbital energy is going to be 0. That means your E value is going to be 1. So this corresponds to a parabola. Okay, now let's say my E value is going to be greater than 0. Then obviously your E value is also going to be greater than 1. So this corresponds to your hyperbola as per the eccentricity studies what we have done so far, as per the conic section and all. Is it not? Okay, now let's say your E is going to be less than 0. Now let me check the entire term is going to be a minus 1. Okay, that means 2h cap square E by mu square m is going to be minus 1. Okay, so that minus 1 plus 1 is going to be what? 0, is it not? So your eccentricity can have 0 value. So that is corresponding to your circle. Okay, how it is going to be circle? Because this term 2h cap square e mu square m is going to be minus 1. Then minus 1 plus 1 is going to be equal to 0. So that is correspond to circle. Okay, now again, if you have a very less than 0 values, if your eccentricity value having 0 less than, or it is very much lying in the range of 0 and 1. Okay, that means if it is lying within the range of 0 and 1, then this corresponds to an elliptical profile. So that is called the ellipse. I hope this is clear. Okay, I hope this is clear for you. If E is very much less than 0, it cannot be equal to 0. Okay, it should be less than 0 and it should be less than 1. So in between you are going to get some range, so that will yield me ellipse. Okay, so this equation is very important when you have a different planetary profiles, and when you are able to find out what is the energy levels. If you substitute here, you're able to predict whether my profile is hyperbola, parabola, circle, or ellipse. So different energy level conditions we have seen. Accordingly, we get the eccentricity values. So that is the beauty of this equation. Okay, I think this concept is very much clear for you, and I expect you to work and get some insights accordingly. Okay, we have done nothing else. We have done some basic physics here and some simplification and other stuff. So I hope this video is informative, and uh, please try to revisit my previous video as well, so that you will get some more understanding of the uh, intermediate steps what I have done here. Okay, so within that we'll wind up the session, and thank you so much. We'll catch up in the next video then.